All right, up until now then, notice that we're not changing the carbon skeleton too much. We're just sort of, okay, here's 4 carbons here, and here's 4 carbons here, and here's 4 carbons, 4 carbons, 4 carbons, right? So I'm just changing the functional groups on the 4 carbon chain. I'm not changing the chain. Now, of course, there are reactions where you change the chain. There are 2 different reactions that we use to change the chain. We can either lengthen the chain or we can cut the chain short. And it's pretty obvious because if you see that you have to turn this into this, you can just count the carbons and see if you're lengthening or shortening the chain. Okay, so in these problems, actually I'm not showing you what you're making, so let's see if we can figure it out. So let's take this nucleophile here, the carbon anion, and I'm going to attack this back side and release that. This is in primary, so this looks like an SN2 reaction basically. And so if I do that, what do I get? All right, guys, for this one, what I get is 3 or 4 red carbons, 1, 2, 3, 4, and then this one's my nucleophile making a new bond right here, and I've got a chain of 1, 2, 3 carbons, 1, 2, 3. And so just count your carbons, make sure that you have them all. 4 plus 3 is 7. 1, 2, 3, 4, 5, 6, 7. And then I also have a halide ion floating around after that. Okay, so that's just an SN2 reaction. Notice that I've got a 7 carbon coming from 2 pieces here. All right, so probably what you'll see is this turning into this, and then you need to know what you added, which is this guy. Okay, so it's good practice to recognize that. So what I usually do is I see this and I think, oh, that came from this part, and then I know this part's new, so I sort of do a squiggly line just to know that these 2 pieces got glued together. So that means the piece that's missing is this 3 carbon unit with something that will make the glue, and that's where you have to know. Nucleophile attacks an electrophile. How do I make this carbon an electrophile? I put something electronegative on it, like an OH or an X. Okay, X is a great leaving group, so I'm going to use that. Down here, we're going to show you how to shorten a bond. We have something called bond cleavage, so you know oxidative cleavage with a strong oxidizing agent like KMNO4 or ozone. In this case, this is ozone. And that's where we do oxidative karate chop through the double bond, right? And so we get 2 pieces from that, and we insert oxygen into each of these double bond areas. Let's do that. Okay, guys, so I basically just cut this in half, put them apart, and then I put in an oxygen right here and right here. And I kept the hydrogens here because this is under reductive conditions, DMS, or zinc in water. That helps me keep these in an aldehyde format as opposed to oxidizing further to carboxylic acids. I'll also include a reaction that I often use, which is a stronger oxidizing condition, which is use hot KMNO4 or KMNO4 and heat. Usually people don't say hot. Okay, KMNO4 and heat and acid workup, and this usually is going to make the carboxylic acid forms of these. So I'll draw that out here. And then some of you guys already know that this is carbonic acid, and that's actually going to turn into CO2 and water. So sometimes you see CO2 and water evolve. So it's going to be this carboxylic acid, CO2 and water if you use KMNO4 heat followed by acid workup. So I really like how Klein breaks this down into just 2 questions. So first, just when you do a synthesis, make a note of how many carbons you're dealing with, and are you lengthening or shortening it in the transformation? Just count. Okay, so second thing is, what are the functional groups? So I need to know if an alkyne goes to an alkene, I need to think of those reactions. If I have an alkyl halide. The tricky thing is with multi-step that you don't know what those intermediates are necessarily, so then you really need to know that map in your mind. You need to know, okay, alkyne going to a ketone or something, or an alcohol, then you need to start linking those together. You might not have one way of going directly. You might have to go to some intermediate or missing link and then use that. So that's really the tricky part, is not knowing what those intermediate steps are. So really focus on trying to get better at that. So one way that you can do that is a toolbox we use, as a toolkit that we use in organic chemistry, is to look at retrosynthesis. Retro means backward. Okay, so, like Throwback Thursday, or, looking back at what could have been a precursor that then you used to, step along. So, for example, let's say, so retro means backwards, so let's start with a product. You're trying to make this, and you're trying to make it from a smaller molecule, okay? And they tell you the smaller molecule is this. All right, so we sort of do a quick assessment, okay? Like I mentioned, are there any changes to the carbon skeleton? Count your carbons. Now I can already tell from the pattern, see this isopropyl group right here? So I know that this part comes from here, this part comes from there, and this triple bond has something to do with that double bond. So that really helps a lot, is just to look at those patterns. And then notice that we added a carbon on here. So this is where I would sort of do a quick thing here and say, oh, wait a minute, there's some carbons on here that are not in the starting material, right here. Okay, so this is just a squiggly line. Again, it's sort of indicating where I need to glue some pieces together. Okay, so that's where this comes from. Is we notice that there's a point here where we need to add a carbon. So what we had was this molecule, and then we added a carbon. Okay, so we take this molecule and we write that down here. So this molecule came from this molecule. Then this molecule, how did that relate to here? Well, remember that idea of addition-elimination? So sometimes you can't go directly into moving a pi bond. You have to add something to it and then eliminate. So that's where we're adding something and we're going to eliminate. And you can do that for alkenes to alkynes, right? Or alkynes to alkenes. So here we're going to go alkyne, and we got to have something that double eliminated to the alkyne. And then that gives us a link from the alkene. So the alkene reacted to this alkyl halide, and then this alkyl halide got double eliminated into an alkyne. So I'm highlighting the functional group transformations that are needed, and then retrosynthetic analysis tells us what those, helps us to determine what those intermediate or missing links are. Okay, so let's take this idea, okay, and let's write out the answer to this problem. So the answer is, well, first the question was, how do we go from this starting material to this product? And using retrosynthetic analysis, we know we go from here to here to here to here. So take a moment and just make this into a problem for yourself. We're starting with this molecule. How do we go to this molecule? And the answer is going to look like 1, 2, 3, 4, blah, blah, blah. However many steps it takes, you write those reagents out. Okay? You can write them all over the arrow, or I just split them up. I put some above and some below. It doesn't matter. I guess technically they should all be above, but it doesn't matter. But what I would like you to do is get in the practice of not just writing out your answer, but showing it. So go from here and show each step. What are the reagents it takes to do each of these things? And then write them above the arrow, okay? And that will help you learn these as you go. All right, guys, so we're back, and first step is BR2, and if you want to put a little, solvent here that's aprotic, like methylene chloride or carbon tetrachloride, that's fine, or you can just leave it blank, as long as you know that it's aprotic solvent that's not interfering in the reaction, that's fine. Now, something that I noticed while doing this, and maybe you did too, is that our goal is to do this alkylation step at the end. So it requires NaNH2, which we're already using to do the double elimination. So I don't really want to protonate this. I want to keep it negatively charged so that I can then attack here, right? So I don't really need this neutralization step here. Okay, so I'm just going to keep my NaNH2 excess. That will keep this in the negatively charged form that I need to attack my methyl halide. You can specify the halogen as iodine or bromine or any kind of good leaving group, okay? And one mistake students make is they put RX. I don't want R. I want you to tell me what the R group is. That you need to say that it's methyl halide, okay? You need to say it's methyl bromide or methyl iodine, okay? So even X is not ideal. You should just say, you know, just say what it is, okay? CH3Br, methyl bromide. All right, so the steps are going to be number 1, Br2, number 2, excess Na, NH2, strong base, and step 3, methyl iodide or methyl bromide is fine. All right, and so that's all you need. All right, so let's work through each part of this reaction map and see if all the steps make sense. So here, our first step is a strong base. It's considered a small base, even though it's ethyl group. We use it just like we use hydroxide. And so to eliminate Zaitsev, I grabbed that hydrogen here and then lost it like that. And so that's how I'm going to get this Zaitsev. And then another alternative is to use HBr and peroxide to go from here backwards, and so that makes sense. I'm going to add that to the less substituted carbon. Okay, that's fine. And so that works by radical mechanism. And just to review, you know, there's the HBr, and then this. And then we also know if we have a bulky base that we're not going to get the internal hydrogen because of steric hindrance. So we're going to prefer to take the terminal hydrogens out on the end here. So we'll make an alkene that's terminal. We'll make the alkene here as opposed to here, which is the Zaitsev product here. Okay, so that makes sense, I hope. And then if we want the Br, instead of being anti-Markovnikov, we want it Markovnikov. We just don't use the peroxides, just use HBr. And here, if we want the Br over on this carbon on the end, we haven't seen that yet, then you can start with this alkene and do your anti-Markovnikov. So make sure that you know, okay, that if you want the Br here, you need a double bond here. To get a double bond here, you have to get the terminal here with the bulky base. If you want the internal double bond, you can have a choice of Br here, or you could have a choice of Br here. So really get to know all of your options. And really, there's just three reactions you need to know. HBr, okay, Markovnikov, HBr and peroxide, anti-Markovnikov. Those are both with an alkene starting material. Or alkyl halide, do elimination, either with a small base to get Zaitsev or with a bulky base to get the Hofmann. So those are just really simple reactions. So in order to get a terminal alkene, we used a bulky base, tert butoxide. And this is potassium tert butoxide. A lot of students ask me, what the heck is this? So TBU is tert butyl, so 3 carbon methyl groups on a carbon. The oxygen is the oxide part, and that's negatively charged. So that's really the base we're talking about. Instead of hydroxide, it's a tert butyl group instead of the H, okay? And then the potassium's just the counter ion. Just like how we use sodium hydroxide, we use potassium hydroxide. That's just a counter ion. And then to make the less substituted alkene, and then here I think I made a mistake. I think I meant to ask about the more substituted alkene, but assuming that it's the less substituted alkene, I use potassium tert butoxide. If I want to make the internal alkene, the more substituted alkene, or the Zaitsev product, then I need to use either sodium hydroxide or sodium ethoxide, as in this example. And I'd like you guys to know that you can use any of those. You can use sodium ethoxide, sodium methoxide, or just sodium hydroxide. They're all considered small bases, and you won't really need to know the difference between these for synthesis until next quarter, where it does make a difference which one you use. Let's work through this reaction map as well. So we have an alkene turning into an alkyl halide, and this is Markovnikov addition. So I want to make sure that I use HBr without peroxides. Then I want to do the terminal alkene, so I use the bulky base to get this one reacting rather than the internal here or here. Okay? If I want the internal, then I need to use a small base like sodium methoxide, hydroxide, or methoxide. All right. This pathway is with the anti-Markovnikov addition. So now I want to have options of having a double bond down here. And to do that, I need to recognize this is less substituted than here. So this is a Hofmann elimination. So I need a bulky base for that, because these hydrogens out here are more accessible than this hydrogen in here. So the double bond's going to form that way. And then to do elimination on this internally, I need a small base to grab the hydrogen in here. So then I'll use sodium methoxide. So the critical step that determines whether the pi bond is external to the ring, like this, or internal inside the ring, really came from this step here. You have to first get reactivity on one of those terminal carbons, so one of these two carbons. So we do that with a Markovnikov addition. And then we got to do an elimination externally using a Hofmann elimination, so bulky base. All right, and then NaOH produces the same product from two different alkyl halides. What are we talking about here? So we're talking about this part here. So these two bases here, this base here, you have two different alkyl halides and they're forming the same alkene. And that's because this is a small base that makes the Zaitsev product, right? So that's the more substituted one. So instead of using this methyl group out here, the hydrogens out here, we're going to use either this hydrogen here or this hydrogen here. And it doesn't matter which one, it's going to make the same product. And this one as well, it's going to use a hydrogen here. It's only one option, so it's going to make the internal alkene. So it's really based on the fact that you're using a small base and there's only one Zaitsev product possible due to the placement of either of these Br groups. All right, so now we're ready to practice some of these things on our own. Okay, so using everything you've learned, let's see if we can step through this multi-step synthesis here. And I want you to think back to those two questions, right? About the carbon chain, is that changing? And are you lengthening or shortening it? And then what are the functional groups that are changing? So first, what I would say is let's see what parts of this, you could sort of see already that this part is the same as this part, and then this part here is the same as this part here. So what you're trying to do is change the reactivity of there to here. So across this bond, you want to change it so that it's on this end. So we have the same number of carbons, which I've outlined in red. So we're not doing any ozonolysis, we're not doing any alkylation. We're just going to change the functional group placement. So we're changing from here over to this end here. So to do that, in my mind, I'm thinking I need to step this over to this carbon here, and then from this carbon, I need to make reactivity here, and then I'm going to step it over to this end. Okay, so to do that, I need to do an addition, an elimination, and an addition. So see if you guys can write out a scheme, okay, starting with this. What are all the intermediates you need? And then see if you can fill in the reagents. If you think you've got it, then write them all on this arrow. Okay guys, so what I see is that we have to do an addition, and luckily this is asymmetric, so I can really control it to be in the anti-Markovnikov position. So I'll use HBr in the presence of peroxide, and then I'll add heat or light to get that started. My second step is going to be to get that to make a double bond here. So instead of the Zaitsev, I'm looking for the Hofmann, the terminal alkene. So I need to use a bulky base like potassium tert butoxide, and I'm going to use some heat to get that going. For the third step then, I need to add Br anti-Markovnikov again. So I'm just going to use HBr in peroxides again. All right. So that's it. Okay, so that's not too bad, hopefully. Okay, notice the strategies I used. I tried to see how this molecule fits into this molecule. Did I add carbons or take any away? The answer was no. I'm just changing my functional group placement. So I'm going from the middle carbons to the end carbons and then ultimately to a Br on the end. So this is going to involve anti-Markovnikov, knowing that it's anti-Markovnikov and knowing the reactions for that. Okay, so here are a bunch of practice problems from Klein where ultimately the final answer should just have a step, the steps of the reagents that you need. But for each one, I think it's really great practice for you to write out the scheme. What are the intermediates? And then think about that when you're writing down your list of reagents. Go ahead and give that a try, and I'll post the answer key.